Welcome back. Today we have Arkaprovo with us from B.Math second year with us. His interests are in algebra, and today he will be giving a talk on the insolvability of the Quintic equation. Without further ado, I request you to continue the talk. Thank
Okay, so today I'll be giving a talk on insolvability of Quintic. So, uh, what does insolvability of a Quintic mean? It means that not every Quintic equation can be solved in the radicals. For example, a radical expression is an expression of a form that contains multiplication, subtraction, division, addition, and radical operation. For example, this is radicals. These are radicals. So, we first want to study what exactly radicals are. To study what radicals are, we will look into field theory. And so the first thing I would like to introduce is what is a field extension? Say there are two fields, K and F, and K is contained in F. Then I call F as a field extension of K, and we denote it by this notation. So the key observation here is for a field extension, F acts as a vector space over the field K. And so that vector space has a dimension. I denote it as the degree of the extension. And this I write it as okay. Most the degrees I will be working with finite extensions. I will not be working with infinite extensions. Mostly I will work with finite, but for infinite extensions, you will find it. So I'll give an example of what a field extension is. Say we have these complex numbers and the field of real numbers. This is a field extension. This is contained in this, and both of these are fields. Now, there are ways to extend field. I will show you that. Like, there is a field F, and I want to adjoin something. Say element alpha. I will denote this as the smallest field containing both F and alpha. And it actually turns out this field. It turns out of this field. And you can change that is a field and all the properties are followed. And this is called extension by alpha. Like this is an extension of. So, what are radicals? How do we construct radicals from rational numbers? Say we want to construct this radical expression. We first take, we start with Q. Then we adjoin square root to Q. Then we adjoin this expression. What I did was, first I adjoined the square root 2 because square root 2 square is 2. This is in this field. Then I adjoined this element as cubing this makes us come back to this field. And extensions like this, I will call this a two radical extension because squaring this 2 will give us an element back in here. And I will call this three radical extension as cubing this element will give us an element in here. So basically, any radical expression can be reached by chains of such radical extensions. Then there is some element alpha which can be expressed in forms of radicals. Then I can build from Q a field K1, field K2, Kr, such that alpha into this field using such radical extensions. So this is N1 radical extension, this is N2 radical extension, N3 and so on. We can take N is equals to N1, N2 till Nr minus 1, and all the extensions will be N radical extension. So I'll keep this fact aside as result each radical. Like we can build a tower of such extensions. Okay. Okay. Now I will move on to some definitions that will be used in the proof, like minimal polynomials and okay, maybe before minimal polynomials, I will talk about what Galois extensions are. So, uh, an extension, this is an extension of a Galois. K is an extension of F. F is a subfield of K, so I will define this as field orthomorphisms from F to F, sorry, from K to K, fixing F. Now, what does this mean? These are basically functions from K to K such that f of alpha is equals to alpha for all alpha belongs to F, and f of A plus B is equals to f of A plus f of B, and f of AB is equals to f of A, f of B. So this is the definition of a Galois rule. Now, what is the definition?
Actually, what do you mean by automorphism?
Yeah, automorphisms are basically functions from algebraic object to another algebraic. An algebraic object is the same algebraic object, preserving the algebraic properties of that object. Like for example, we have a field here, and the field's properties, if A, comma B belongs to F, then A plus B also belongs to F. These are fields, so A plus B also belongs to F, so F of A plus B equals to F of A plus F of B. Likewise, so the addition operator is conserved. Again, here the multiplication operator is conserved. So that is idea of what automorphisms are in general. But in here, this is the definition of what automorphisms are. These are the part describes automorphism, and this is an extra condition for Galois. Now, I will define this splitting field of a polynomial. Say f is element of fx. This fx means the ring of polynomials over the field set, as in the coefficients are from the field here. Then splitting field f of f is just smallest field containing f and all roots of the polynomial f. As it turns out to be f of alpha 1, alpha n, where alpha I is the roots of the polynomial f. Now I define what is the Galois of the polynomial. This is a definition of Galois of a polynomial. Uh, what? Why am I considering this definition? The consequence of this definition is that the Galois consumes the f, roots of f in a certain way. How does that happen? Like, say, sigma is an element of Galois f, and alpha is the root of f, as in f alpha is equals to 0. Then what happens to sigma alpha? Say f is of the form summation k x to the power k from 0 to k. Then this is of the form summation k sigma alpha whole to the power k from 0 to n. Now, because of this property, this multiplication and this addition, we can take out the sigma summation k equals to 0 to n k sigma alpha to the power k, which is equals to summation k equals to 0 to n sigma of summation k alpha to the power k. And this is just f of alpha, which is sigma f of alpha, which is equals to sigma of 0. And because sigma fixes f and the field f contains the element 0, this is exactly 0. So what we found out was, if alpha is the root of f, then also is sigma alpha. Okay, so this part of the board is, I will not use this part because it's very light. This is equal to 0. Okay. So that was the Gauss polynomial. It permutes the roots of the polynomial. Now what is a minimal polynomial? A minimal polynomial alpha x is the minimal. Okay. So what is this? These are the this is a minimal polynomial such that alpha is the root of this polynomial, and this is an element of fx. Such a polynomial always exists because this extension, I assume it to be finite. I assume this extension to be finite. If such a polynomial does not exist, then it will be that alpha to the power 0, alpha to the power 1, alpha square, this forms a linearly independent set. So one such polynomial works like this. Okay. Now, before moving on, I would like to introduce what a Galois extension is. This was a definition of Galois groups, and normally we consider Galois group over Galois extensions. When an extension is Galois, there there is a bijection between the some this group and intermediate field. Subgroups of this group and intermediate field, and that is known as the fundamental theorem of Galois theory. I will show that, but before that, what is a Galois extension? K over L is extension can only if two conditions are satisfied. The first is normality. Which will be for all polynomials f in fx such that x is irreducible. If there exists alpha in the k such that f of alpha is 0, then all roots of it are in K. So what says simply is, if for any irreducible polynomial f in fx, there is one at least one root in K, all of its roots lie in K. And the second condition is separability. This just says that all roots of area alpha have multiplicity 1 for all alpha in K. So all the minimal polynomials have roots of multiplicity 1. Okay. Now, why is this definition useful? I will not prove the fact, but there is a big theorem, the Galois, that is the fundamental theorem of Galois theory, and it states that if these two conditions are satisfied, then fundamental theorem of Galois is an extension E over K is Galois, then there exists a bijection between subgroups of all E over J to intermediate fields of E and F. What this means is all E over F is just gal E over F. So gal E over F. So what is the bijection? Since H is a subgroup of gal E over F, then H gets mapped to e to the power H. And e to the power H is defined as the fixing field of H, which is E in the field E such that H of E equals E for all H in H. This is a map from subgroups of Galois equivalent to intermediate fields of E and H. And the other way is map say K is contained in E and is contained in F. So K is an intermediate field contained in E and F. Then map K gas E over Q. I just turned out this is a bijection. And this is a very useful thing because we are working in fields which are infinite objects and sometimes very hard to deal with. Two groups which are finite objects, like I am only considering, okay, one thing I should mention is E over F is a finite extension. If it is not a finite extension, the study of implicating is quite different and the theorem is also different. So this is a finite. Okay. So I just wanted to introduce it as a why Galois extensions are useful, but this will be useful much later. There is also something more about this paper that I will tell while I will do the proof of something that I'm not going to. Okay. So I'll start with my first theorem. Let a field F be a subfield of C such that zeta n is in F if alpha belongs to C such that alpha to equal n is in N, then if alpha over F is Galois extension and gal if alpha over F is cyclic. Cyclic just means it is generated by a single element. Like there is a stigma such that a power of it can generate any element. So how to prove it? So for the Galois extension, I need to prove two conditions, normality and solvability. For normality, say if alpha to the power n is beta, and we know this beta is in N, therefore x to the power n minus beta, this is an element of x. Actually, we only need to take this polynomial. This is an explicable polynomial method, and we only need to take this. So x to the power n minus beta is of the form x minus alpha, x minus beta and alpha, then x minus beta and alpha, and minus alpha. This is a factorization. So, what is F alpha? F alpha is basically splitting field of say fx is this polynomial, then this completing field of F as this is equals to f of alpha comma zeta and alpha comma zeta is equal to minus 1 alpha. And zeta and alpha are already there, so these two are same. So this uh, right, I will need to verify the normality and separability. So for normality, we can check that this splits into linear factors and all alpha, zeta, and alpha, zeta square, and minus 1 alpha. All of them are in base alpha. So this extension is a normal extension. Similarly, for separability, the only minimal polynomial we have to check is minimal polynomial of alpha in it, and that will be differential by minus beta. Same there, only one multiplicities are there. So both normal and separable extension. And now for how do you do Galois at alpha over F time. So I prove that F alpha is splitting field of F. Therefore, F alpha over F, Galois proof of this is just the Galois proof of the polynomial. And we know the Galois proof of the polynomial permutes the groups. Here we can construct the homomorphism from Galois F alpha over F to this. This is a cyclic group that will generate a zeta, and the map will be the map from this to this will be say sigma is the equivalent of this, and sigma alpha is alpha zeta n to the power k. Then I map, then this mapping psi. Then I map psi of sigma to zeta to the power k. So sigma gets mapped to zeta to the power k. Uh, Two things you have to check, that is in the group homomorphism, and you will also have to check that this map is an injective map. For group homomorphism, you have to verify that this psi sigma 1, sigma 2 is psi sigma 1, psi sigma 2. And for injectivity, you can use the normal way. So you can check that. As it turns out, this homomorphism is an injective homomorphism. So this group is isomorphic to a subgroup of the cyclic group. And because of that isomorphism, we can say that this group is also cyclic, because any subgroup of cyclic group is also cyclic. So this group turns out to be cyclic group. And that group is our level. Okay, so I will give it. Now I will define what is the composite of fields. This diagram just means F1 is a subfield of F, F2 is a subfield of F. And the composite of F1 and F is smallest field containing both F1 and F2. This is the smallest field containing both F1 and F2. This exists as we can take intersections of all states containing F1 and F2. So this is a compositum of two fields. One immediate observation is that compositum of splitting field of N with N is splitting field of N of N, where N is a field extension of F. This happens because this is F alpha 1 field alpha N, and I take the smallest field containing all the roots of F and F and L, because F is a subfield of L, that is all the roots of alpha and L. So that is exactly the definition of this. Okay, now I'll be putting the most important theorem that we'll be using here. That will be let if comma k comma a is equal to c such that if something of k and if some field of L and k over f is finite value. Basically, what the picture comes out to be is this C these are the extensions that we'll be working with. And I have stated that this is Galois. K over N is Galois. So what it will turn out to be this thing. This will also turn out to the theorem is that this will turn out to be Galois. Then what KL over L is Galois. And 2, this Galois group of K over L will be isomorphic to Galois group of K over K intersection L. And this will be a subgroup of okay. So to prove this, I will uh, first use the fact that K over F is a finite Galois extension. As K over F is a finite Galois extension, so this is a proof. Proving one, say dimension of K over F is N. Then consider a base alpha 1 till alpha n of K as a vector space over 6 with a base. And then clearly K is F alpha 1 alpha n. Now consider some polynomials fs. which would be product of all the minimal polynomials. Should be also product of all the minimal polynomials. Then we know that K over X is gamma. We know that K over X is gamma, and as this minimal polynomial ms alpha I, this annihilates alpha I, and alpha is an element of K. Alpha I is a K. So this completely splits into linear factors in K, as in all the roots of L are in K. Because all the roots are in K, the splitting field of L is contained in K. It is contained in K. And as x minus alpha 1 then x minus alpha n, this divides x as x minus alpha divides same as alpha x. This tells us that f of alpha 1 till alpha n is contained in splitting field f of n. And this two are same, so this is equals to k. So we already have this is a subset of k. So the splitting field of f is exactly k. So we got that splitting field of f is k. So I will run this. We will not make this. We'll only get the factor splitting field of f is k. Now what is k here? So k is splitting field of f into L. And as f is a subfield of L, this is splitting field of L. So what we want to do is look at K over K L is gamma, which means splitting field of F over L over L is gamma. We want to see that this expression is gamma. The way to do that would be to first check normality and then check probability. For normality, the proven simple. This is an observation that an inverse polynomial divides all the polynomials which has alpha as a root. The reason for this is related to you can choose it without lemma and but take this as a fact. So okay, these polynomials are in elements. Polynomials with two elements. As n is a subset of L, this implies n is alpha I of x also belongs to Lx. And because this annihilates alpha I, ml alpha I x divides ml alpha I x. Now, as k over f is gamma, as k over f is gamma, all of these roots splits into all of the roots of this polynomial splits into linear factors, as in all of the roots are contained in F, or contained in K. All of the roots of this polynomial are contained in K. So all of the roots of this polynomial are contained in K. And as Kn is a higher extension than K, and it also contains L, this polynomial splits completely in splitting field of L, as this is K. So that checks normality for us. For separability, we want to check if there are multiple roots or not. Say Cx is summation a to x to the power k, and we define a formal derivative p prime is as summation a to x to the power k minus 1 k from 1 to n. And we know that if there is a multiplicity, say p is an irreducible polynomial, and if there is a multiplicity alpha in a p, then both p alpha and p prime alpha are zero. So what happens is, if suppose there is a multiplicity alpha, say p alpha is equals to p prime alpha is equals to 0, and we know that the minimal polynomial will divide both of this. Minimal polynomial must divide any polynomial that is annihilating with alpha. So we get that ml alpha of x divides px. But px is irreducible. So this will be exactly equal to this. It cannot be equal to 1, otherwise it cannot annihilate alpha. So it must be exactly equal to this. Now this polynomial also divides p prime. And this polynomial is equal to x. Therefore, px divides p prime x. Because this is equal to mn alpha x. Right? So this must divide p prime x. And p prime x is 1 degree less than px. So p prime x is exactly 0. But if p prime x is exactly 0, this implies summation k a k x to the power k is equals to 0, which implies k a k is equals to 0 for k belongs to 1 to n. But this now we use the fact that all of these fields are subfields of the complex numbers. Because these are subfields of the complex numbers, like in other fields like Z mod field, FP, which is Z mod Z, it may be that field equals to 0. But for fields like this, which are called characteristic 0 fields, there exists an inverse of P, and this k equals to 0 just means that AK is 0. And AK is 0 means this Px is a constant polynomial. But P alpha is 0, therefore both P and Px is 0. Which means that there is a contradiction, there is no polynomial like that. So if there exists a double root, then we get a contradiction. So there must exist any double roots. So that is separability follow. And so we have proved that this here over here is gamma. And that this first part of the theorem. Now I will prove this, and to prove this, I'll set up an automorphism again. An automorphism phi, a homomorphism phi from automorphism, Galois group of KL over L to Galois group of K over L. And the automorphism will send an element sigma to its restriction over K. Now, first I will prove that this automorphism is this homomorphism is an injective homomorphism. For that, I will look at the kernel of this homomorphism. Phi of sigma is arbitrary, which is sigma such that sigma related to K is arbitrary. And we know sigma is coming from Galois K over L. So sigma already fixes all elements of L. So this basically means that this is elements of sigma of the form sigma fixing K and sigma fixing L. So both of these are identical. Now, as both of these are identical, uh, it is coming from K by L to Galois K over L. So both will fix both the field K and both the field S. So the composite of it also fixed. So this is basically just the identity. So the kernel is trivial. And the kernel is trivial implies that this homomorphism is injective. And for the second part, how do we calculate what the image of this homomorphism is? To calculate the image, I'll prove that sigma of K belongs to K for all K naught belongs to K. Sigma of K naught belongs to K for all K naught belongs to K. So, suppose for contradiction, sigma K naught is alpha and this is not in K. Then we look at the Riemann polynomial of K. This as this K naught is in K naught is in K, this minimal polynomial splits completely, as in all the roots of this minimal polynomial are in K. But if we apply sigma to this, as sigma fixing L and F is a subfield of L, this turns out to be now we can actually calculate this by using the properties of homomorphisms. And we know that sigma k naught is alpha. So we get that this is 0. This is 0. Sigma of 0 is minimal polynomial from k naught of alpha. And sigma 0 is 0. Therefore, alpha is also a root of minimal polynomial of k naught. But by normality, we know that that can be true because alpha is not an element of K and we know all roots are elements of K. So, by contradiction, sigma K naught belongs to K. Therefore, this math sigma to sigma respected to K has an image Galois K over K intersection L. Now, how this happens, how I concluded it from this map is that this map sends this map sigma restricted to K is a function from K to K. I just want that it maps elements of K to K. Also, sigma fixing L because it is an element of Galois K over L. So this all of these are being elements in L are being fixed here. So sigma of beta is equals to beta for all beta belongs to K intersection L. That is exactly Galois of K over K intersection L. Now, by the isomorphism theorem, we can say that Galois of K over L is isomorphic to Galois of K by K intersection, and that is the subgroup of K by K over L. Okay. So, so now I will be needing the fundamental theorem of Galois theory again. So I'll state it again. As I stated, there was a bijection between subgroups of Galois groups and intermediate field. But one thing more is there, that is, if there is an intermediate field K such that this is a Galois extension, this is a Galois extension, and then Galois group of E over K is the normal subgroup of Galois group of E over N if and only if K over is Galois. So this the group subgroup corresponding to this is normal if and only if this part is a Galois extension. This was the point that I did not mention, and I will be using this in the proof of this following. Okay. So the theorem states that if K over F is a Galois extension and L over N is a Galois extension, given that L over F has a abelian Galois group, which just means all the elements of the Galois group commute, like sigma 1, sigma 2 is equals to sigma 2, sigma 1, and here the non-abelian Galois group, which means not all elements commute, and it's a simple. What does a simple group mean? It states that there is the only normal subgroups of that group are the entire group and the identity element. So, using FPGT, if this is an abelian Galois group, then Galois group of L over Galois group of this is given. This is subgroup of Galois L1L, and the interesting thing that happens for abelian groups are all subgroups of that abelian group are normal. So this actually turns out to be normal subgroup. And because it's normal subgroup, by this fundamental theorem of Galois theory, we can say that this is a Galois extension. Therefore, this is an again by applying the fundamental theorem of Galois theory, now this group, the Galois K by K plus experiment is normally Galois K over F. But Galois K over F we are assumed to be a non-abelian simple group. And simple groups, the only normal subgroups can be itself and the identity element. If this is equals to the identity element, this implies all the automorphism fits everything. So K intersection N is equals to K. And this just implies A plus subset of K. But that just shrinks the diagram to a straight line. And we are not studying groups like that. The other option is possibility is that if you think Galois K over K. And if that happens, then F is K intersection N. And if F is K intersection N, then what it turns out to be that right, we're equivalent this theorem, right? Galois K over N is isomorphic to Galois K over K intersection N. So I'll keep this result that okay, I don't need this. I will use this board for the next part. So much demonstrate. So what we have found out that F is equals to K intersection L. F is equals to K intersection L. And by this theorem, Galois KL over L is isomorphic to Galois K over K intersection L. Now this is exactly Galois K over K. Okay, so we got that if we have a structure like this, then what happens is this Galois group and this Galois group are same, and this is isomorphic to Galois group of K over N. So the consequence of this is if there is a structure like this, there is K, there is KL, there is K, there is L, there is K intersection L, and there is L. Suppose this group turns out to be alternating for phi in phi, and this group turns out to be our abelian. this turns out to be an abelian group, then this also is isomorphic to A5. Because A5 is a simple group. This is a corollary of this theorem, and this will be the thing that helps us prove the insolvability of a quintic. And the key factor here is that A5 is a simple group. As in, there are no normal subgroups of A5 other than A5 and identity. So now for the proof of the final insolvability of a quintic. Remember, we have constructed such a tower. So let f be a polynomial in Fx, and f is a subfield of C. Because all the things I have proved, assuming it is a subfield of C, and the degree of f is 5. Suppose there exists alpha such that it is solvable by radicals. So there is such that it is solvable by radicals. Therefore, there exists a tower KR, KR one, K2, K1, and this K1 is rational number, and this alpha is KR. And we also assume that f of alpha is 0. And this alpha is a root of, we have assumed that it is solvable by radicals, so such a tower not exist. Now, what is the or this I used to write such theorem on it. Same n is equals to written field of f over K. So n is a splitting width of f over K. Then this n is an extension of Q, right? And this n K2 is an extension of both n and K2. Now, suppose I just find some n such that this happens. Galois of splitting field of Q of f over Q is isomorphic to A5. If I can find that f such that this happens, then also this splitting field of f and Q is a Galois expression. If I can find such an f, then we can get A5 here. This is a Galois extension. This is also a Galois extension. Okay, now one thing I should do that all this, these are n radical extension, and as in alpha to the power n, like if this Q contains zeta, say all of these are n radical extensions, right? If by using this theorem, all of these are, say this is zeta and all of these are n radical extension Q zeta n, then all of these are cyclic groups by using this theorem. But there is an extension for this. Actually, we must start from T, not T zeta. So all of these are cyclic. Is this cyclic? Not necessarily. This need not be cyclic. But the thing is that this always turns out to be this extension Q zeta n. This also turns to be an abelian. And because theorems are abelian groups, we can work here. So this is K2 is actually Q zeta n. and then we construct the radicals. We don't take the radicals first. First we can choose eta, then we try to construct the radicals. So this is a Galois aggregate. And this A5 is a simple non-abelian group, and this is a Galois extension. So we can actually jump A5 to this by this theorem. Similarly, we can jump in the next step because all of this forward is cycling and cycling groups are abelian groups. So finally, L KR minus 1. Oh, and one thing, this L K2 is just splitting field of K2 of L Kn equals to splitting field of K of L by induction. Because L was splitting field of Q of F, and by that L K1 is L K2 is just splitting field of K1 F K2, which is equals to L K2, and this is equals to splitting field of, and this is equals to splitting field of K2 of F. So by induction of the splitting fields. So finally, at the top, we are LKR and KR. So and this is A5. This group is isomorphic to A5. So all we got is that sense. Galois group of LKR over KR is isomorphic to A5. Alternating group of 5 elements. And as I said that this LK equals to splitting field of KF, LKR equals splitting field of KR of F. So this is just Galois group of splitting field of KR is over KR. And by definition, this is equals to Galois group of KR, Galois group of polynomial S. And the polynomial, because alpha is a root of the polynomial, then fx equals to x minus alpha gx. Now, if my degree of f was 4, so degree of g is n is a Quintic polynomial, so there is a Quintic polynomial. Degree of g is 4. Because alpha is already an element of Kr, this splitting field of Kr f is just the splitting field of G over Kr. Because alpha is careless, so that is the same thing. Therefore, Galois group of Kr A equals to Galois group of Kr G. And there are only 4 roots of G. Therefore, the Galois group permutes only 4 roots. Therefore, it must be a subgroup of the symmetric group of 4 elements. And so, by the cardinality, must be necessary because of 4 factorial. But we know this is isomorphic to A5. By the tower is getting this is isomorphic to A5. So, what we get is that cardinality of A5 is equals to 4 factorial. And this is actually a contradiction. This is 24 and this is 60. And so the contradiction is that not always there exists an alpha. Like if we can find an L such that the splitting field is A5, like also one another observation is it true that there exists a polynomial such that this is isomorphic to A5? Maybe there are no Quintic polynomials such that this is isomorphic to A5. But as it turns out, there does exist polynomials like that. And what is this? This Galois group splitting field Q of F over Q is just Galois of F over Q. So are there polynomials F such that Galois of this if it turns out there are like for example x to the power 5 plus 20x plus 16. I'm not proof with this, but this polynomial actually turns out to be using Galois of F. We can calculate that more simply than we can try to exhaustively search. There are infinite many polynomials, so we can't exhaustively search all the polynomials. So that completes the proof. And if I wanted to give a review of what I did, I first looked at the first key observation was how does the radical look like and how can we construct it using field extensions. Then I introduced what a Galois was and why it was useful because of the distinction between fields and groups. Groups are actually more studied than fields. Fields are more complex structure than groups, and even in when the extension is infinite, there is a study of Galois theory, and that is some topological properties are imbued on the extensions to get the Galois groups of the extension. So this completely goes, and if anyone questions.
So, uh, thanks to us for the talk, and